We will now do the shear and bending moment diagram for a continuous beam containing 5 reactions. Okay. We first start off by cutting the beam up into 6 parts. We will write 6 different moment equations. And we will recognize that the beam has 3 redundant reactions. But first, we find the degree of indeterminacy of the beam. We see that the beam has 5 reactions, and we cut it. We don't have to cut it into any part. We can just leave it as continuous.
5 reaction, 3 equation, 1 piece. Second
so
degree.
3.
Second
So
degree.
it's the second degree of indeterminacy.
Yeah.
Okay? Cool. That's our step 1. We want to find the degree of indeterminacy. Now we want to cut it into 6 parts. We want to cut it. We're going to draw another diagram, another representation of this beam. We're going to draw there's a cut over here. Let's cut M1. There's another cut between the 50 kip load and the reaction B. By the way, these are reaction A, B, C, D, E. Okay? So, between reaction A and B, there's one moment. There's moment 1. Between reaction B and the 50 kip load, there's moment 2. Between reaction 50 kip and
C.
And reaction C, there's
Another
moment 3.
Yeah.
Between moment C and the other 50 kip, there's moment 4.
Yeah.
Between the 50 kip and reaction D, there's moment 5.
Yeah.
And between
D and E.
D and E, there's moment 6.
Yeah.
Okay. Now, we write out an expression for moment 1. You see at moment 1, there's 2 kips per foot.
Carlos, you can use the whole board.
Yeah.
And when you write, don't stand in front of it.
Alright. For moment 1, there's a 2 kip per foot distributed load. So we write 2
Times X.
times x1
Yeah.
times x1 divided by 2
Times moment.
minus
Moment.
100. Well, we have to do something first, which I just forgot to mention. Something that is very important. We have to take away all the redundant reactions. The redundant reactions are reactions B, C, and D. So we come up with our real beam. Or we can just take it away from over here to make our lives easier. Let's just take them off over here. See, we're making our lives easier right now. Okay? So in moment 1, we do some statics work. We have these 50 kip, 50K, 50K. We have the distributive load over here, which is 30 feet long. And we have the other one that is 30 feet long. $30 feet, 30 feet. Okay, now we do some statics. We have all of our external reactions, and we find our reactions at the supports, at the two outer supports, and they're both 110 kips. So now we can write out our expressions for moment 1. Moment 1, we have the distributive load of 2 kips per foot, so we write 2 times x1 times a half times x1 minus 110 kips times x1 plus m1. That's our cut for 0 to 30 feet. Okay? Now we write our expression for moment 2. Moment 2 is from 30 to 45 feet. We write out negative 110 times x2 plus 2 times 30 times x2 minus 15 plus m2 is equal to 0. When we put it in simplest form, our m2 is 50x2 plus 900. That's our second moment expression for the real being. Now for our third expression, we write out negative 110 times x3 plus 2 times 30 times x3 minus 15. The x3 minus the 15, they're inside of parentheses, by the way. Plus 50 times parentheses x3 minus 45 plus m3. And we end up getting that m3, the m3 is equal to 0, right? We end up getting that, all of this is it has to be equal to equilibrium to 0. So when we do that work, we end up getting that m3 is equal to 3,150, and that's the expression for moment from 45 to 60 feet. Now, we go to the other board, and we write down our expression for a moment of 4, and we get the same thing. 3,150 kips per feet, and we have 45 times x, we have from the range of 45 to 60 feet, x4. M5, we go from 30, we're working backwards now. We're going from this part to this part for the fifth one. So we're going to start off from the displacement of 30 to 45 feet. Because this, notice that in this distributive load, we go from 0, we're going backwards to 30 feet. Then this portion right here is 15 feet. So we go from 0 to 30, 30 to 45. The difference between 30 and 15, the difference is 15 feet. No, the difference between 30 and 45 feet is 15 feet. Okay?
Carlos, take a break. 1 second.
So for M5, we go from 30 to 45. We write down M5 is equal to 0, equal to 110 times x5 minus 2 times 30 times x5 minus 15 minus M5. This whole thing, as I just mentioned, is equal to 0. So you end up, when I put it into simplest form, I end up with M5 is equal to 50 times X5 plus 900. Okay? That's from 30 to 45, in going from the
Right to left.
right to left. Yes, right to left. I should just write that for the other ones. Right to left.
No, it's clear, it's clear.
Okay. Now, also going from right to left, we have M6 equal to 0, being equal to 110 kips times X6 minus 2 times X6 times X6 divided by 2 minus M6. And when I simplify that, I end up with M6 is equal to negative X6 squared plus 110 X6. And this is in the range of 0 to 30, going from right to left. Okay.
Carlos,
Okay.
now you have your 6 equations. Just
Yep.
write them on one board and you can erase the rest.
All right. Now we have our 6 equations.
I'm going to pause here.
So these are the simplified versions of our 6 moment cuts in the real beam. Now we're going to do our moment cuts for each unit load of the redundant reactions. The unit loads, as aforementioned, will be 1 kip, a 1 kip imaginary load at each reaction point. So we will now make cuts for each of those regions. We will leave, for your convenience, we will leave the real beam expressions here on the board. Now we will do the expressions for the first unit load beam. Unit load 1. We will have 3 unit loads for each redundant reaction. So we have right where reaction B is occurring. We have that a 1 kip load down. We do some static so we get the reactions of the end supports. We get 0.75 and we get 0.25. Now we have our 6 moments. M3, M4, M5, and M6. So now we do our expressions we write out our simplified expressions. We have from 0 to 30. Our expression is moment of 1 is equal to 0.75 times x1. For our second expression, for our second moment, it will be from 30 to 45 feet. Our M2 is equal to negative 0.25 x2 plus 30. For M3, we go from 45 feet to 60 feet. So for M3, our expression is equal to negative 0.25 x3 plus 30. For M4, we're going from, again, from 45 to 60. We're going from 0.25 times x4. Let me write this neater, x4. And 5. We have 0.25 times x5, which is going from 0 to 30, apologies. It's going from 30 to 45, from right to left. This is for your viewing benefit of what I've done so far. So for M6 is going from 0 to 30, from right to left on the beam, right to left. And M6 is equal to 0.25 times x6. Now the reasons I did not explain how each thing broke down exactly is because from the previous videos and from previous examples, it's been gone over of how to obtain each portion of each moment. So now we will go to the second unit load reaction B. So reaction at C. Our goal is to arrange everything coherently, so that because you want to keep everything organized. You want to keep everything organized. You want to do your bookkeeping done. This is all about the bookkeeping now, because we know how to make the cuts and stuff. We know the physics of a fit now. We just make the cuts. Now we're doing the cuts for unit load 2. Then we will do the cuts for unit load 3. Then we will combine them, find our deflections at point B and point C, etc. Now, we will carry on with unit load 2. Unit load 2, we have this beam. One kip reaction acting over here. We have 2 supports going up at 0.5 kips. Since this is acting right at the midpoint of the beam plane. Okay, and again we have our 6 different moments. Moment 1, moment 2, moment 3, moment 4, moment 5, moment 6. Okay, so we write our expressions. We have from 0 to 30. 0.5 times x1 from 30 to 45. We have from 0.5 to x2. For M3, we have from 45 to 60. 0.5 times x3. For M4, we have from 0.5 to x4, and it's going again from 45 to 60. Because we're going from right to left. From M5, we have from 0.5 to x5, we have 30 times x5, 45. Then we have M6, we have 0.5 times x6, 0 to 30, going from right to left. Okay, these are our expressions for unit load 2. Now, unit load 3. We're getting exhausted already, but we have to do this. Remember, it's all about the bookkeeping, people. It's all about the bookkeeping. Okay? In my own personal opinion, I say we do slope deflection, but we have to also learn how to do it with flexibility method. So we put our imaginary one kip load at point D. And we do some statics and we get 0.75, 0.25. Okay? So again, we have our moments. M1, M2, M3, M4, M5, M6. Let me write this a little cleaner. Want to be neat as possible, organized, so let's write this over here. Okay. M4, M5. We put our one kip load over here. Yeah, one kip load. Okay. So again, we do what we've been doing for the past 20 minutes or so, writing our moment expressions. 0 to 30, we have moment 1, 0.25 times x1. From 30 to 45, we have moment 2 is equal to 0.25 times x2. For 45 to 60, we have M3 is equal to 0.25 times x3. for the force moment, which is going from 45 to 60 from right to left, we have 45, 60, yeah. Negative m4 is equal to negative 0.25 x4 plus 30. And 5 is equal to negative 0.25 x5 plus 30. Going from 30 to 45. From the right to left. And for m6, going from 0 to 30. We have 0.75 times x6. Okay. So we have all of our expressions.
Tell them, remember these numbers, now we're going to do integrals.
Remember this, have these numbers written down because we will need them to do our integration. So now we're going to do integrals.
And pause.
Okay, ladies and gentlemen, take out your calculators, your laptops, anything, your formula sheets, anything. Although I don't recommend formula sheets because I met somebody one time who thought that he was very wise and he thought that it was intelligent to put all your formulas, even the whole textbook, in your formula sheet. I don't recommend that for structural analysis. It takes you nowhere. So, I will show you, now we are going to obtain the deflection equations for at the reaction points at B, C, and D. Okay? So now, before that, I want to go over these three formulas. So we have delta B plus by times FBB plus CY times FBC plus DY times FBD. And that same algorithm repeats itself for all the other reactions, for reaction C and for reactions D.
Perfect.
Now, delta B is our displacement at reaction B, and which we will be doing now in the integration process. By is the reaction that we want to obtain. FBB is the cut on the unit load multiplied by itself at reaction B. This is for the unit load 1. Unit load 1, as far as I'm concerned, was the unit load for reaction B. So what we do is that we take the cuts, all the cuts for the unit load of reaction B, and we multiply them by itself, and then we find the integration at each region. So that's FBB. FBC is when we multiply all the cuts for the unit load of reaction B times the unit load of reaction C, and FBD is when we take all the unit loads moment expressions from reaction from unit load B of reaction B, and we multiply them by those of the unit load at reaction D. And the same thing iterates for the other two expressions, equations. So now we will find the deflection at point B. Yes, we will find the expression at point B. Okay? So we have delta B is equal to limit of integration 0 to 30 parentheses negative x1 squared plus 110 x1 times 0.75 x1 over EI times dx plus integral 30 to 45 50 x2 plus 900 times parentheses negative 0.25 x2 plus 30 over EI times dx plus integral 4560 3,150 times parentheses negative 0.25 x3 plus 30 over EI times dx.
Thank you.
Plus integral 30 to 45 50 x5 plus 900 times 0.25 x5 over EI dx plus integral 0 to 30 negative x6 squared plus 110 x6 times 0.25 x6 over EI times dx. What do we get at the end? We get the answer to be 3,453,750 E over I. That's our deflection at point B. For deflection at C, we have our expression 0 to 30 negative x squared plus 110x times 0.5x over EI times dx plus the integral 30 to 45 parentheses 50x plus 900 times 0.5x over EI times dx plus integral 45 to 60 3,150 times 0.5x over EI times dx, and we get that our deflection at point C is 4,843,125 over EI. Okay? And the deflection at D is equivalent to the expression at B due to symmetry. So we write that down. We write that down over here. Deflection at D is equivalent to deflection at B. Okay? So now that we have this, now that we have these deflections, we write down our FBBs, our FCC, our FDD, our FBC, our FBD, and our FCD. Okay? So we multiply the cuts at for unit load at reaction B. So we have FBB equal to, we have integral 0 to 30, 0.75 square over EI times dx plus integral 30 to 75 parentheses negative 0.25x plus 30 square over EI times dx plus integral 0 to 45 integrals parentheses 0 to 25 x square over EI times dx, and we get that to be 20,250 over EI. Okay? Now we have FCC equal to integral 0 to 60 0.5x square over EI times dx plus integral 60 to 75 parentheses negative 0.5x plus 60 square over EI times dx plus integral 0 to 45 0.5x square over EI times dx, and that gives us an FCC of 36,000 over EI. Now we have FDD. We have integral 0 to 75 0.25x square over EI times dx plus integral 30 to 45 parentheses negative 0.25x plus 30 square over EI times dx plus integral 0 to 30 0.75 x square over EI times dx is equal to 20,250 over EI. Now we multiply our unit load moments at reactions B times C together. Then we do the same thing for the ones at BD and the ones at CD. So get these down. We have them down. Now we're going to write the ones for BC, BD, CD. FBC equal to integral 0 to 30 0.75 x times 0.5x over EI dx plus integral 30 to 60 parentheses negative 0.25x plus 30 times 0.5x over EI times dx plus integral 60 to 75 parentheses negative 0.25 x plus 30 times negative 0.5 x plus 60 over EI times dx plus integral 0 to 45 0.25x times parentheses 0.5x over EI times dx. And this is going to be equal to 24,750 over EI. Okay? For FBD, we have integral 0 to 30 parentheses 0.75x times 0.25x over EI times dx plus integral 30 to 75 parentheses 0.25x plus 30 times 0.25x over EI times dx plus integral 30 to 45 parentheses 0.25x times negative 0.25x plus 30 over EI times dx plus integral 0 to 30 parentheses 0.25x times 0.75x over EI dx. And this all adds up to 15,750 over EI. And now for FCD. Finally, the last one. We'll erase these. For FCD, we have integral 0 to 60, parentheses 0.5x times 0.25x over EI times dx plus integral 60 to 75, parentheses negative 0.5x plus 60 times 0.25x over EI times dx plus integral 30 to 45 parentheses 0.5 no, excuse me, parentheses 0.5x times negative times, okay, for this one is the integral is 30 to integral 45, and we're multiplying parentheses 0.5x times negative 0.25x plus 30 over EI times dx plus integral 0 to 30 parentheses 0.5x times 0.75x over EI times dx, and we end up getting 24,750 over EI. Okay? Now, we do something similar to what we did with problem 1. We plug in what we had for our delta B, our FBB, our FBC, and our FBD, and etc. We plug it into the three equations, and then we can use our calculators to solve the system of equations, which will throw out at us our reactions BY, CY, and DY. And from there, once we get our reactions, we can do our shear diagram, and we can do our moment diagram, and we can also do our deflection diagram, which is what we're going to do next. Okay? So now we're going to plug in all the numbers onto these three equations. Okay, so now we have 0 equal to 3,453,750 plus BY 20,250 plus CY 24,750 plus DY 15,750. And then for our second expression, we have 0 equal to 4,843,125 plus CY times 19,800 plus BY 24,750 plus DY 24,750. And 0 is equal to 33,453,750 plus DY 20,250 plus BY 50,750 plus CY times 24,750. Now you plug this into your calculators. I won't cover that because I assume that you guys know how to use your calculators to put in system of equations, and we get that by is 63 K, cy is 47.9 K, and dy is 63 K. Okay? So now we know all of our reactions, so we put them down over here. Well, we know our reaction for B, C, and D, so we can just do statics now. To obtain these two external ones, which we found to be 23.05 K at the ends. Now we do our shear moment diagrams. First, we're going to start off with our shear diagram. We'll erase this.
Yeah, you can read it. Yeah, read it. Okay. Oh, is that marker good?
Yeah. For our shear, we have starting from 23.05. We see that there's rectangular distributive load, so it's going to change linearly. It's going to bring it from 23.05 all the way down to negative 36.95. Then it's going to bring it back up to 26.05. Then it's going to be constant. Then it's going to bring it down to negative 23.95. It's going to be constant. It's going to bring it back to 23.95. Then it's going to be constant. It's going to bring it down to negative 26.05.